I'm David Driggers, CTO of Verari Systems, and I'm here to talk to you about why vertical cooling, why Verari, why we chose to take a different tact and a different way of cooling our systems compared to the general populace out there. 6 years ago, Verari took a more holistic look at the data center. Rather than designing from the server out, we started looking at the challenges and problems that we were seeing within the data center and decided to design from the data center in. One of the biggest challenges we saw was density. As systems were becoming far more powerful and more dense, there just wasn't enough space being allocated to cool the systems. In a typical environment, hot row, cold row environment, there was only a single floor tile in front of a rack that was supposed to cool a rack. The rack sat on 2 floor tiles, had a floor tile behind it for servicing and 1 floor tile in front of it to actually deliver cold air. But we found very early on that 1 floor tile couldn't give us enough cooling. And we started seeing this in our competitors' products as people would put a high density platform like a blade architecture, but then only put 2 of them into a rack. Why? Because they couldn't cool them from within 1 floor tile. We set out to fix this problem. People didn't want to change their density. They still wanted to be as dense as possible. So we looked at where could we get more air from. If we increased the number of floor tiles in front of the rack, that wasn't going to help us because that would decrease our density. Instead, we said, let's get the air from underneath the rack. We've got free square footage there. 2 floor tiles directly underneath the rack where we could actually draw air from. Also, it just happens that the law of thermodynamics says that hot air rises and cold air falls. By taking air in at the base of the cabinet, we were going to actually get the coldest air in a data center. And so we designed our vertical cooling technology. We actively draw air in at the base of the cabinet. Doesn't matter if it's a raised floor or a slab floor, the coldest air in a data center is going to be at the floor. At the first level, prior to entering the cabinet or prior to entering the nodes, we have a row of fans. Those fans actively draw either directly from underneath if it's a raised floor environment, or from the front or the back, or both sides, depending upon if you're in a hot and cold row environment or a cold row environment. We're capable of taking in air from any aspect that the room really mandates. The air is then pushed, actively pushed up through the nodes. We have anywhere from 2 to 4 rows of blades. Cooling is a function of volume more than it is of temperature. Delta T is derived from the amount of volume of air that moves across a given cooling component, so a heat sink or memory modules or hard drives. In our case, we control the volume. Compared to a typical 1U, which uses about 30 CFMs of air, our system within the same data center providing the same amount of air, will wind up being exposed to over 100 CFMs of air. Right off the bat, we're dealing with 3 times the airflow, 3 times the volume of air to work with. This makes it far easier for us to cool a system in our blade architecture than for us to cool even within our own 1Us and rack mount systems that we build. And the reason why? Volume. We're working with a lot more volume, and we're working with guaranteed volume. In the case of typical rack mount servers, you're stacking them on top of each other, and you're hoping that one's not going to affect another one or reduce the airflow and volume. Typically, when you rack and stack 1Us, you'll see a dramatic range in the amount of airflow that goes into the 1Us, with the ones near the bottom and the very top getting up to 40 and 50 CFMs of air, and the ones near the middle getting only 20 to 25 CFMs of air, due to the fact that you can't control the fan speeds based upon the volume that's going into the system, and you're just having to deal with whatever pressure is there and whatever air temperature is there. Typically at the base of the rack, it's nice and cool. At the top of the rack, it's usually quite hot, especially if you've got blowback coming from a hot row or from the ceiling. In our case, because we completely isolate our air intake to the bottom and our air exhaust out the top, we have a very controlled air column that we know how to work with a lot more volume of air. Therefore, our delta T's are actually lower in a blade system than what you typically see from rack mount systems of a similar configuration. Even when you have more machines, our blade architecture is in excess of 2 times the density of your typical rack mount, and yet we have a lower delta T. And the delta T is fully controllable based upon the fact that we can control the fan speed. If you're in a data center where you've got a very heavy load and you need to increase the volume, we're capable of controlling the fan speed, increasing it, enabling the system to draw more air to it. If you're in a data center where the airflow is necessary to keep it low and you've got a lighter load, you can speed down the fans and set them to a point where you're using just the least amount of air possible to keep your delta T where you'd like it to be. One of the other big reasons why we went to a vertical cooling system was we actually looked, so after looking from the data center out, we then started looking inside the actual rack and inside the nodes to try to determine how much power was being used for the actual fans themselves. And we were pleasantly surprised and pleased to find out that this method of cooling, this vertical cooling technology that we had developed, not only was far more efficient from a cooling perspective and actually keeping the nodes with a lower delta T, but also used far less power per server, per node, to actually cool the systems. By using large industrial fans at each level, we wound up having a much more efficient power per fan or power per server than what we were typically seeing within our rack mount systems. By simple comparison, in a lightly loaded rack, which we call lightly loaded, under 20 kilowatts, most people would go, wow, that's so high. But at under a 20 kilowatt rack, we typically use about 15 watts of fan power. That's 15 watts per server to move the air through them. If you take a look at a typical 1U server, that number will be 60, 70, 80 watts of fan power to move the same air, or move a smaller amount of air over the same server. And thereby you have the significant savings of power to move the air through the system. You wind up with a much lower delta T. And anytime you're talking about more volume, you're talking about a higher degree of reliability. So we wound up with a system that was denser, far more efficient from how much fan power is being used to cool the system, a system that wound up being far more reliable. We're seeing the failure rates on our rack mount versus and these are our systems, our rack mount versus our blade architecture, the same components, and a failure rate that's nearly half that of the rack mount. The blades are that much more effective at using the power to cool and the power to keep the systems in a nice shape and nice conditions.